The discovery that electrons can behave as if they are moving through a fourth dimension of space, even while remaining firmly anchored in our three-dimensional reality, sounds like the premise of a science fiction novel. Yet this is precisely what a team of physicists at the Massachusetts Institute of Technology has achieved, and their findings, published in the journal Nature, represent a monumental leap in our understanding of quantum materials and the very fabric of reality. By engineering a new class of materials known as Moiré crystals, they have unlocked a synthetic dimension, a mathematical construct that allows electrons to explore a higher-dimensional quantum world. This breakthrough not only challenges our conventional understanding of space and matter, but also opens a tangible pathway to realizing theoretical predictions that have existed for decades, from higher-dimensional superconductivity to novel topological states of matter. To grasp the magnitude of this achievement, one must first understand the peculiar world of Moiré materials. The term moiré itself is borrowed from the world of textiles, referring to the intricate, shimmering patterns that emerge when two fabrics with different thread counts are overlaid. In physics, this concept is applied on an atomic scale. Researchers create moiré materials by stacking atomically thin, two-dimensional sheets of materials like graphene, a single layer of carbon atoms arranged in a honeycomb lattice, with a slight twist or misalignment between them. This twist creates an interference pattern, a moiré superlattice, which is a new, larger periodic structure that dramatically alters the behavior of electrons moving through it. For over a decade, these moiré materials have been the darlings of condensed matter physics, yielding a treasure trove of exotic quantum phenomena, from unconventional superconductivity to the intricate quantum fractal known as Hofstadter's butterfly. However, a persistent bottleneck has been the painstaking, labor-intensive process of creating them. Researchers would exfoliate atomically thin flakes using Scotch tape, painstakingly stack them with precise twists under a microscope, and etch them into tiny devices, one at a time. This method, while effective for discovery, was fundamentally unscalable and limited the potential for real-world applications. The MIT team, led by Professor Joe Czecholski, has shattered this limitation with a radical and elegant solution. Instead of building moiré materials layer by layer, they enlisted Mother Nature's help to grow them as bulk crystals. They discovered a chemical synthesis route for a class of crystals, a ternary compound of strontium, tantalum, and sulfur, known as a bulk moiré metal, where the moiré superlattice is built into the very structure of the crystal itself during its growth. This is akin to moving from a world where every book must be painstakingly hand-copied to one where entire libraries of encyclopedias with pre-printed, interfering patterns can be produced in a single print run. The result is a scalable, reproducible method for creating high-quality moiré materials, a crucial first step toward harnessing their extraordinary properties in next-generation electronics, sensing, and quantum computing. But the real magic, the wow factor that has captivated the scientific community, lies in what happens to the electrons within these newly minted crystals. The moiré superlattice generated by the two interfering atomic lattices is not just a simple pattern. Mathematically, it is equivalent to a four-dimensional superspace lattice. This means that the electrons moving in the crystal are not just bouncing around in a three-dimensional landscape. They are acting as if they are moving through a fourth spatial dimension. This is where the concept of a synthetic dimension comes into play. It is not a physical dimension we can point to in our world, but a mathematical one that emerges from the material structure. The equations that describe how the electrons move are four-dimensional. To uncover this hidden reality, the researchers performed detailed studies at the National High Magnetic Field Laboratory in Tallahassee, using some of the most powerful magnets on Earth. When a metal is placed in a powerful magnetic field, its electrons trace tight orbits that reveal the shape of the Fermi surface, a sort of map of all the possible quantum states an electron can occupy. For an ordinary metal, this map is relatively simple. But for the moiré crystals, the quantum oscillation data was bafflingly complex, revealing more than 40 distinct frequencies arrayed in a perfectly regular comb-like pattern. This data didn't correspond to anything in the three-dimensional structure of the material. The obvious explanations, magnetic breakdown, quasi-particle interference, were exhausted one by one. The only framework that could make sense of the data was a four-dimensional one. The electrons, guided by the 4D superspace lattice, were hopping along this synthetic dimension. Each hop corresponds to a step along the fourth dimension, and each step generates a new, distinct oscillation frequency. When you line all these frequencies up, you get the remarkable cone pattern the team observed. As co-lead author Kevin Knuckles metaphorically put it, the team's measurements uncovered shadows of an emergent four-dimensional landscape upon which the electrons live. By analyzing the three-dimensional silhouettes of these shadows from different angles, they could reconstruct the four-dimensional landscape that was guiding the electrons. One of the key mechanisms enabling this journey into a synthetic dimension is quantum tunneling. This is a well-known quantum phenomenon where a particle, like an electron, can pass through an energy barrier that, according to classical physics, it should not be able to overcome. It's a bit like a soccer ball at the bottom of a hill spontaneously appearing at the top without being kicked. In a Moiré crystal, an electron in one valley can quantum tunnel out. However, this is no ordinary tunneling event. Once an electron tunnels within the Moiré crystal, it acts as if it had traveled to a completely different world and come back again, as if it had been transported through that fourth synthetic dimension. The electrons are still physically located in the 3D crystal in the lab, but their behavior perfectly simulates a four-dimensional quantum world. This discovery is not just a mathematical curiosity, it is a profound scientific and technological milestone. It provides the first realistic materials platform to test long-standing theoretical predictions about higher-dimensional quantum matter, predictions that were previously confined to the realm of abstract mathematics. For decades, theorists have predicted that higher-dimensional systems should support entirely new phases of matter, such as exotic forms of superconductivity and topological states with properties that cannot be expressed in our three-dimensional world. These are the holy grails of condensed matter physics, and now, for the first time, scientists have a tangible way to explore them experimentally in a laboratory. The implications for technology are immense. The quest for ever more efficient electronics has led physicists to explore unconventional avenues for controlling electron behavior. This new family of materials offers a path toward engineering quantum behavior by designing the environment the particles move through, rather than by altering the particles themselves. The ability to create these materials in bulk, with consistent properties, is crucial. Hand-assembled Moiré devices are finicky, with tiny variations in twist angle or strain-producing crystals with vastly different properties, making systematic experiments difficult and scaling to practical devices essentially impossible. The new bulk crystals, however, grow with a coherent and reproducible Moiré superlattice, offering a plausible route toward Moiré-based electronics. While the path from this fundamental physics discovery to a commercial device is not short, and significant obstacles remain, the team has demonstrated a crucial proof of concept that overcomes a long-standing bottleneck in the field. This discovery is also deeply connected to the rich history of physics at MIT, a hotbed of Moiré material discoveries. It builds upon a decade of pioneering research, from the 2014 discovery of Hofstadter's butterfly in graphene boron nitride Moiré systems to the 2018 breakthrough of unconventional superconductivity in magic-angle, twisted bilayer graphene, and the 2024 discovery of fractional charge effects without a magnetic field. The work of the Textile lab is a direct continuation of this lineage, but it takes the field in a dramatic new direction by introducing a new synthetic dimension to the landscape. The tool has changed, the scale has changed, and the dimensionality, at least for the electrons, has fundamentally changed. The researchers are careful to emphasize that the fourth dimension is synthetic. It is not a real physical direction, but a mathematical construct encoded by the structure of the crystal. However, for the electrons, this distinction is irrelevant. The physics is real and measurable. The electrons in these crystals propagate in the synthetic dimension just as they do in the world's three physical dimensions, and the magnetic field reveals the fingerprints of this synthetic dimension in the observable quantum oscillations. As Nisarg Paul, a co-lead author on the study, explained, mathematically, the equations describing the electron dynamics in these crystals are four-dimensional. The electrons stay in the lab, their behavior doesn't. The future of this research is incredibly exciting. The team will explore how a wide variety of material properties might benefit from these extra synthetic dimensions, which are now within reach of realization. It's fascinating to consider what may be possible next, said Professor Chekolsky. There are long-standing theoretical predictions for higher-dimensional conductors and superconductors, for example. Materials of this type may offer a new platform to examine these experimentally in the laboratory. The higher-dimensional landscape the electrons navigate is, at the moment, mostly uncharted. The theoretical machinery exists, but the experimental constraint has been the absence of a material clean and reproducible enough to test it. The new crystals may be the material that finally opens the door to this strange new world. The discovery is a powerful reminder that reality is far stranger and more complex than we can perceive with our senses. It is a testament to the power of human ingenuity to peer into the hidden depths of the universe by creating materials that give form to mathematical ideas. This is not just a discovery. It is the birth of a new field of physics, one where we can engineer dimensions to unlock the most exotic secrets of the quantum world.